Hello students, welcome to all aspiring engineers in my YouTube channel presented by Professor Priya Shimpe. In this video, we are going to study the bridge rectifier. In this, the content will be bridge rectifier, its block diagram, a simple block diagram, its circuit diagram and explanation, and how the waveform is generated in bridge rectifier, and the list of formulae for bridge rectifier. You know what do you mean by rectification? The process of converting AC into pulsating DC, the process is called as rectification, and the electronic component which does this rectification, we call it as a rectifier. Now, 4 diodes will be used in bridge rectifier. Let us see first a very simple block diagram of bridge rectifier. In exams, they also write the abbreviation of bridge rectifier as BR. A bridge rectifier, you can see it is a type of a full wave rectification. At the input of a rectifier, we are always going to connect the AC signal. When the AC signal is connected to the bridge rectifier, it gives you a full wave rectification. A full wave rectification, that means it allows the positive cycles to flow in positive direction and the negative cycles, they change their direction into the positive cycles. So why we are getting a full wave rectification by using bridge rectifier, that we have to study. We will see its circuit diagram. In the circuit diagram, if you see, a step down transformer is used. Bridge rectifier, it requires step down transformer. It no longer uses center tap transformer. So here the 4 diodes are used, D1, D2, D3 and D4, in such a way that these 4 diodes are forming a bridge. Now what do you mean by bridge? Means the D3 and D2 are parallel with each others, while D1 and D4, they are parallel with each others. The opposite pair of diodes are parallel with each others. That means the voltage in D1 will be equal to the voltage in D4, while the voltage in D2 will be equal to the voltage in D3, and that is how we called a bridge rectifier. They are forming a bridge. If you see between the points or the node, C node and the D node, we are going to calculate our output voltage. Here I have connected a bulb. You can also redraw the load resistance RL. Let us see. You can draw such a circuit diagram in your books, right? You can write down the diode names, anything as you wish, but see the direction of opposite diodes must be the same. See how these diodes are kept here, right? And D3, the direction of D3 and D4 must be the same, right? If I see this point, this is a junction or a node. This is a node forming at point A, right? At point A, here the D1 diode, its anode is connected at point A, while it will be the cathode terminal of D4. This is how, if you keep the diode direction, then and then only the full wave rectification is possible. If you see from the below, the secondary winding, its lower point is your B point, the B node. At this B node also, here it is the anode terminal of D3 diode, while it is the cathode terminal of D2 diode. This is how we have connected the 4 diodes in a bridge. And yes, across the load resistance RL, we are going to calculate the output voltage VO. Let us see its operation one by one. As you all know that the diode which is used as a rectifier, the diode behavior with the positive cycle is always different than the behavior in the negative cycles. Now let us see one by one the behavior of the bridge rectifier with positive and negative half cycles. Let us see it first. When at the primary winding we are applying positive cycles with an amplitude of plus Vm volts, your D1 diode and D2 diode becomes on, and that is why they have shown here as blue, right? So D1 and D2 diode are on. See the direction of the current, right? The current has started to flow through the bulb, and that is how the bulb glows in the positive cycle, because of D1 and D2 diodes are on, right? And at the primary, now I am applying the negative cycles. When I apply a negative cycle with the maximum amplitude of minus Vm volts, now my D3 and D4 diodes are on. So that is why these are shown in blue, because they both are in the negative cycles. My D3 and D4 diodes are on. And see the direction of the current, right? Once again, the current is flowing through the bulb, and that is why in negative cycles also the bulb glows, right? So why this happens, let us see in deep, right? So when I apply positive cycles at the primary, right? The point A, this is the point A, right? This is the point A of your secondary winding, and this bottom point is the B point of your secondary winding, isn't it? So when we apply positive cycles, a positive voltage is induced in your secondary winding between the voltage VAB, right? Between these 2 points, between the point A and the B, here also the voltage is induced is positive, plus Vm, right? So that means if you see the maximum voltage is appearing at the point A, so I write down A as A point is having positive potential, right? From the bottom, your B point has a negative potential. So that is why your B point becomes negative potential, right? So what happens if you see B is negative, and at this B point I have connected diode whose negative terminal is connected. So that is why from the B point, which is negative, and it is connected to the negative terminal of D2 diode, and that is why negative your D2 diode gets forward bias. Let us see the case from upper side. The point A becomes positive, and this A point, it is connected with the positive terminal of the D1 diode. So that means positive of diode is connected to the positive potential, and that is why your D1 is on. It becomes forward bias. And that is the reason when we apply positive cycles between the points A and B, your voltage VAB is positive. That means your point A is positive with respect to point B, and hence D1 is on and D2 is also on. If I redraw this circuit, the diode D1 is on. It is allowing the current to flow after the 0.7 volts if the diode is made up of silicon. Same, the D2 diode is on. It is allowing the current to flow after the 0.7 volts. Right? And if you see, the D3 and D4 are reversed bias. D3 and D4 are reverse bias. Why they are reverse bias? Why they are reverse bias? Because if you see here, it was the negative terminal of the diode, like this diode was connected here previously. Isn't it? This was the direction of the diode connected. When the point A becomes positive, it is the negative terminal of D4 diode, right? So negative and positive, right? So that is why your D4 get reverse bias, and we have replaced by open switch, right? If you see from the bottom also, here this is how the diode was kept previously. At the B point, which is getting negative, this negative voltage gets connected with the positive terminal of D3. So the positive of D3 terminal gets connected with the B point, which is negative, and hence your D3 has become reversed bias. So that is why your D3 and D4, they are becoming reverse bias and they are replaced by open switches. Okay, so as you know that current always flows from higher potential towards lower. So the A point is a positive voltage. So the current from the secondary winding, it flows through the point A, and D1 diode is ready to allow the current to flow through it. At this point, D point, the current will never come towards D3 because it is not giving any path. The current flows through RL, right? Current flowing through RL, it is IL, right? Then it goes towards, the current will move towards the point C. It will never go towards D4 because no path is there. From the C node, the current will be flowing through D2 diode because it is giving a path. Through the D2 diode, the current will go back to the secondary winding. Right? Here I haven't drawn the complete circuit diagram. Right? This is your secondary winding. The current will move from the secondary winding and it will flow in this closed loop path. This is how the current will flowing in a closed loop path when it is a positive voltage, positive half cycle is applied. Okay. So that is why you see the output voltage, it is the voltage drop in RL when the current flows through RL. See, the current direction is coming from upwards. So that is why output voltage, it's positive polarity in upward direction and the negative will be below. And that is why you are getting an output voltage VO is equal to Vm minus 1.4. Why 1.4? Because it is the addition of the two diode barrier potential. 0.7 of D1 diode and 0.7 of D2 diode. 0.7 plus 0.7, that is your 1.4. Clear hai? Let us see the bridge rectifier in negative cycles. Whenever at the primary winding you apply negative cycles, right? A negative voltage is induced. A negative voltage is induced between the points A and B. Right? So the voltage between point A and B is negative. That means what will happen? What will happen? Your point A is negative and B is positive. The point A is negative with respect to point B. So see, your A is negative and B is positive, right? So what happens? A point is connected with D4 whose negative terminal is connected. And now the negative, your D4 diode becomes forward bias. If you see from the bottom, your point B is positive. Here we have connected a D3 diode whose terminal is positive. So that means positive terminal of the D3 diode gets connected with the positive potential, and this is how your D3 diode now it turns on with the negative cycles. While your D1 is off and D2 is also off. Let us see the current direction in it. Right? So D1 diode is off, D2 diode is off. Your D4 diode is ready to allow the current to flow after the 0.7 potential. Here D3 diode is also on. It will allow the current to flow after the 0.7 volts. As you all know that A point is negative and B point is positive, right? Current always flows from higher potential towards lower. Now the higher potential is towards B point. So from this secondary winding, the current has changed its direction. It has moved towards the B point. Because B is having the higher potential. Who is ready to allow the current? Your D3 diode is allowing the current to flow through it. At this point D node, the current will come once again. It will flow through RL, and see the direction of the current. It remains the same as it was in the positive cycle. So that is why the current is flowing in this direction. Here you are getting a positive voltage and here is negative of your output voltage. Now the current flows through RL. It will go through this wire. It will be moving towards, this current will move towards the point C, the node C. It will never come in D2 because no path is there. Your D4 diode is ready to allow the current to flow, and through A point it will go back to the secondary winding. So this is how the direction of the current flowing through D3 and D4 diodes in negative cycles. right? So in the positive cycle, we are getting a positive voltage. When you are applying the negative cycle at the primary or at the secondary, still you are getting a positive voltage. The voltage in this bridge rectifier will be equal to Vm minus 1.4 if the diode is made of silicon, right? So you can see, if I compare a half wave rectifier and a full wave rectifier whose output is equal to Vm minus 0.7, and bridge rectifier is giving you VO is equal to Vm minus 1.4. The bridge rectifier gives you minimum output voltage as compared to half wave and a full wave. Why? Because here only 0.7 is getting subtracted, but in bridge rectifier 1.4 is getting subtracted. So that means the output voltage VO in a bridge rectifier will always be a minimum value as compared to VO in half wave rectifier and full wave rectifier. If I take an example, if I consider Vm is equal to 5, your bridge rectifier and full rectifier, how much it will be giving you the output? 5 minus 0.7, which is equal to 4.3 volts, right? But if I calculate for bridge rectifier, the bridge rectifier will give you 5 minus 1.4. How much it will be? 3.6 volts. The which circuit is giving you the least output or the minimum output? Yes, 3.6. Your bridge rectifier gives you the minimum output. Right? So this is the output voltage. VO is equal to Vm minus 1.4 for a bridge rectifier. And the maximum current, here it is Vm upon Rs plus 2. The 2 factor is getting multiplied. 2 into Rf plus RL. Why the 2 factor is getting multiplied? Right? Because the current is flowing through 2 diodes. In negative cycles, it will be flowing through D4 and D3. That means we have to calculate the resistance, forward resistance in both the diodes. So, twice RF means it is the forward resistance in both the diodes, whether D1 and D2 or D3 and D4. Okay. So see, this is the input voltage. This is the secondary winding. This is the secondary winding voltage waveform. Between the secondary windings, point A and B, first we will get a positive cycle. For this positive cycles, your D1 and D2 are on, and you are getting an output is equal to Vm minus 1.4. Right? In the next cycle of the secondary, that is a negative voltage applied between the point A and B. For the negative cycles, your D3 and D4 diodes are on. It will allow the current to flow, right? While D1 and D2 is off. And here the maximum voltage will be equal to Vm minus 1.4. And that is how, because of D1 and D2, D3 and D4, you are getting a full wave rectification. Okay. This AC waveform, it repeats itself, and yes, you get a repeated full wave rectification. It continues unless and until you have applied AC signals. The operation continues. And these are the formulae for a bridge rectifier. If you see these formulas, this is very much similar to your full wave rectifier with center tap transformer. Why both the formulas in both the circuit remain same? Because in center tap transformer, full wave rectifier and a bridge rectifier, because their waveform is same, and that is why their formulas are the same, right? Here I have forgotten to edit this load resistance at the output of bridge rectifier. It must be here, bridge rectifier everywhere. Clear hai? You have to memorize these formulas. Thank you.